where it goes through 2, and the other case where it goes through 3. All right, so those are my 2 critical paths I have to look at. If you have something in parallel and the same number of transistors, it's going to be the same size. In case of A and B, they're going to be the same size. All right, but C, A, and B are not going to be the same size. You could already guess that A and B are going to be 2 times as big as C. Because right now, the length for A and B, if you look at it as a single transistor and model it something like this, it's going to have 2 times the length because it's twice as long. So therefore, it's going to have twice the width to match up back to what a regular transistor would look like. All right, so you could already guess these are 2 times as big as that. Let's say you don't. So then what we're going to do is, like I said, the ones that are in parallel with the same number of transistors are going to be the same. So these are going to be the same. So I'll call that N1, N1. And then you'll notice because it's 2 in series, so then this is going to be N1 as well. This is going to be N2 and N2. All right? And it's the same mainly because it's going to be, they're the same type of transistor, the lengths are going to be the same. Same idea, same logic between these 2. They're just going to be twice as long. Okay.
So C is going to be the same as A and B, and
C is going to be the same. Same logic is between A and B. And it's because it's just going to be twice as long, so then it's going to be twice the width. So in this case, it's just twice as long, twice the width. And it's just that you happen to have 2 in series that they match up. All right? So we got to go 1 over N0, and we'll go the first path. The first path is going to be 1 plus N1 plus 1 plus N1. And it's just these 2 in series, or these 2, whichever route you choose. And that's going to be 2 over N1, so cross product or whatever you guys do, will be N1 equals 2 N0. So for this, it would be 2 and 2 and 2 for the ratio. Second path, now we're going to do, going through these 2 transistor A and B, it's going to be 1 and 0 equals 1 over N1, which is this first A, plus 1 over N2 plus 1 over N2. Combining like terms, I have 1 over N1 plus 2 over N2. All right, we know what N1 is because we just solved for it. So then it's going to be 1 over 2N0 plus 2N2, 1 over N0. If you try to solve for this one first, you'll notice that you're stuck in terms of N1, so you have to use another equation to solve for N1 in order to solve everything else. Or else you gotta have 2 unknowns in one equation. All right? Now you have this, you move this over, so you have 1 and 0 minus 1, 2 and 0 equals 2 and 2. This, simplified, times 2 on top, 2 on bottom. 2 minus 1 is just going to be 1 over 2 and 0, 2 and 2. Cross product, then you get N2 equals to 4 and 0. So these are going to be 4 and 4. Alright, so the steps I took is 1, find paths of different transistors. What I mean is different lengths in transistors. So it doesn't matter if I go A or B. All you have to do is pretend you're standing at the end, right? And you're saying like, okay, I want to see how many transistors I have to go through. And if you're standing here, there's one way where you could go through 2, and another way you go through 3. All right, so then you have 2 equations that you have to solve for. All right, yeah?
If you go through the path with 3 NMOS first, then you have different sizes.
If you go to the path with 3 NMOS first, you notice you gotta have an N1. You can't solve N1. So then you have to solve something else, right?
You have something like 3 over N. Set 3 over N equals 1 over N0. So then the NMOS of the path of 3 will be the width of 3 NMOS.
I mean, I'm not sure how you would be able to solve out with not knowing what N1 is. know what I mean?
Do I start with that?
Yeah, go for it. Take blue.
Okay.
Here you go.
I'm still confused on why C is the same as A and B done.
It's basically going to be the same because if you look pathwise, right? Pathwise, there's one transistor and another transistor, right? These transistors are the same, meaning in terms of they are initially the same. You don't know what the widths are. But if you look at it, you're going through 2 lanes. All right? So then they have to be the same width. Because it's going to be 2 over W and then has to be the same width. It's just a determination of what you choose first. Yeah, and then it's more like what you chose as your path, right? If you go through, somewhat like what he's saying, is if you choose to go through this path first, okay, I get what you mean now. So if you chose to go through the 3 first, right? Then you're going to say, okay, A is going to be the same as these 2. And then you solve out for the ratio of C. You may get different numbers, but as long as the ratio is the same, it's okay. All right. Does that make sense? Yeah. As long as the ratios are the same. Yeah. Cool. So that's a plausible way as well. So instead of saying these 2 are the same, he says these 3 are the same and go backwards. That's fine too. All right. So any more question on sizing?
Oh, and they all give you the same W again, right?
No, not necessarily. They
I
won't.
mean, both paths, no?
Because this W would give you 3, 3, 3, and then because if you have 3, the ratio of these 2 would be different.
Does that mean that there's
It would be like
multiple ways of
1.5
building that?
actually. Yeah.
There's just multiple ways of building that?
Yeah,
using
there's
the
multiple ways of building it. All right, cool. Personally, I don't like doing the 1/over way. I just like thinking about lengths. Thinking like, okay, this is 2 times length, so 2 times length of this one, and then this will cause 2 times length, multiply from there. It's a more physical background of thinking instead of this 1/over nonsense. So yeah. Okay, putting that aside, onto PTL. So I'm basically going to redo the same lecture he did, but feel free to like stop me at any point because I understand this is a little complicated and it's a little hard to get in the beginning. And I have some examples where I want you guys to come up. Let's do it. Green seems to be strong today. All right, pass transistor logic is literally what it sounds like. You're passing your value through. And the idea is going back to what we had originally thought in the transistor in terms of water faucet and a controller, all right? So this is your current going through, and ideally A will pass through to Y if B allows it to turn on. Meaning if A allows the current in terms of saturation or trial, B would go through, all right? Just think of it, don't think of it in terms of your equations, of your current equations, just think of it as this, all right? Another way to think like, okay, how is A a controller as well as B? A is a controller as well. If you really do wanna think of it in terms of the equation, B ds is just as well as a factor of current as you have as VGS once you have current going. So that's why A is able to pass through and so can B. So ideally the logic you want is Y equals A dot B. All right? I'm going to put a capacitor here to store that charge. So we can see that A once B is like steady. All right? So what we notice is ideally our truth table should be all right. So let's do for all the ones where B is 1, where we know B allows it to go through. If B is on, that means A will pass. So Y would equal to 0, and this one will equal 1. All right? But the issue here is, let's say we don't have the capacitor pre-charged to 0, that it has a previous state. All right? So if you have B is 0 and A is 0, so B shuts off the water faucet, but you have a bucket at the end, which is the capacitor. You don't know what the bucket holds if you don't know what the previous stage is, right? So we can't necessarily say Y is 0. Because what if the capacitor was already charged, let's say, to 1 in the previous cycle, and then charged off, it didn't fully discharge, so there's still water in the bucket. Does that make sense? So therefore, we don't know. Same case here. Even if A is 1 and B is 0, you're still blocked at the water faucet. There's no, ideally, there's no water going through, but you don't know how much that bucket charges. So therefore, it's also a question mark. If we took away the capacitor, right? Let's say we took away the capacitor, and you wonder, okay, 0 and 0. If it's 0 and 0, ideally, maybe it worked, but why would it hold the charge for too long? But yeah, anyways, this is an issue with just the capacitor at the end. All right? So what you notice is, output So when it means output must be connected at all times to high and low, it means Y must have an vice versa of B naught of the control. Right now, when you have B is off, we don't know what it is, right? So we must have the vice versa. Same like pull up, pull down. The reason why we have a pull up is to pull up that 1. Reason to pull down is to pull down to ground. And there's always a path for 1 and 0 for the output. Same thing goes for here. You always need a path for all possible inputs, meaning you need a path for when B is on and when B is off. So what do? We just create this dummy logic. All right. This is going to be Y equals to A and B, or secondary pathway of B dot B naught. B dot B naught is going to be 0. So it just cancels everything out. All right. But what it does is it corrects this issue. So when B is 0, so you're going to have 0 here, and you're going to have 1 here. So 1 allows it to flow. While we don't know what this one holds, we'll look at the other branch, and we'll say, okay, 1, and then 0, so it'll pass at 0, for Y will always be 0. All right? And that's just giving you what is missing here. All right? Now comes the idea of CMOS. All right. So the issue here is the same like our VTC. So right now we're only using NMOS. So this is comparable to a circuit with our common source circuit. All right. Our VTC, it will never touch VDD because it always has that voltage cross against that resistor. So it'll always start low, but it'll go down to 0. Assume that's 0. All right. Same thing happens here. Your resistor may not be your NMOS may not have a very good one. So what we have to do is we turn it into CMOS. And what we do is just have the complementary with your PMOS. All right, so what's going to happen is I'll draw it to the side. So it's going to look like and you just gotta have the complementary gate input to your PMOS. Right? Remember how drain and source are interchangeable? So depending on what state you are, the drain and source might flip between these two, depending if it's low or high. For instance, if A is low and Y is high, like remember what I said, drain is always with the highest voltage. So then drain would be here. All right? But in the case of this is low, this is high, this is low, drain would be here. So they'll flip. We'll never ask you to do current calculations with PTL most of the time, so you should be okay. All right? What I do want you guys to focus on for the final is this type of logic with the capacitor in there. All right? Because that's basically storing a value in there. Imagine if we had a switch, right? We store the value, we switched it off. Then you have basically a sampler. So this is like the basic ideology. So he likes to give those. So any questions on the CMOS?
What was the reasoning again, like real quick?
If you have just the NMOS, you're doing something very similar to pull up, pull down, where you only have the NMOS and you can't pull it all the way up to VDD. And it may not necessarily be that one. All right? You may not see any resistance, but there's resistance in the line and whatever. But so what you want to do is have the complementary using the PMOS to pull it down. Yeah, and pull up and pull down all the way. And you just have the complementary input. All right. Cool thing about this is if we go back to this one, can I do it to this one? Yes. Good. All right. If you have the same basic logic flow through and your outputs are just inverted, you're inverted. And then what you have up here is an AND gate, and then this one is an AND. Not inverted, sorry. So that's really cool because considering like, if you imagine if you have to take like, okay, if you add complementary to it, then that's 4 more, but, or 2 more and then 2 more. But imagine if you had to make another NAND gate based off what you have, all you had to do was pull wires down, add 2 more of the same logic. And it's pretty simple. Or basically what you want to do is you don't even have to change it. All you can do is just flip the logic of your input and you could have the reverse. Compared to if you had like a CMOS, you would have to put in an inverter and stuff. And your logic may not necessarily be the same, pull up, pull down for a NAND or an AND. Okay. So, that being said, I will take some volunteers, some brave souls. Or I will start picking people. So basically what you want to take away from this PTL lecture is how to do basic PTL, at least up to this part. And then all you basically have to do from this to this is just put in that PMOS to invert. But most of the time when we say PTL, we're referring to this, not the complementary version. All right? But of course, note the complementary version, the differences each in between them. There are a lot of tricky ways he could give PTL on a test in terms of sticking in this mode and then saying what are the faults, or sticking to this mode, throwing some capacitors here and there. Yeah, so if in the future you guys could look up SRAM, DRAM, he'll go over that in class, and he'll go over it really fast. Like I said, this whole week is taken up by me, but the next week he'll go over SRAM, DRAM, like memory logic, and that's really confusing, and that's for sure going to be on your final. He always does it, and it's always like the one that trips you up. And don't be shocked if he gives you a tau propagation high-low of a memory logic. It's very like that, and then he'll like, or I've seen him do this, which is really hard. Or like he'll have C go to the same B, and he'll tie the caps in between. And then that'll be like really trippy to do when you do tau propagation, low high, high low, especially because you have multiple inputs. So be wary of that. All right. All right. This is taking forever. Whatever. I'll set up a problem. All right. The problem that I want somebody to do is the y equals CA plus CB. Just do the PTL. Don't do the complementary yet. All right. I will pick. No. Who looks like they're paying attention? You asked the question. Yeah. So do this logic. Pick any markers. I should give more colorful markers. Maybe they'll get more students to come up. I'm not looking. Or not use green. Green seems to be the problem here. Alright. Yes. That'd be Y. Okay, start with the first branch. C and A. Yeah. And then out inputs.
This was a 1, right?
Yeah, that's good. That's good.
That's not a 1.
No, it's on logic. Yeah. Okay. Now you've got the basic ones.
Okay.
So what are some issues with this design? You could tell me initially.
Week 1.
So you want to make a complementary?
I mean, you asked for PTL, so.
Yeah, and then just name what you see as weakness. The ones and zeros. And there's also the weakness. Remember when we did the first with the capacitor, there's the weakness of when your C is strong. Oh no. Remember the issue with your C inverted, right? And then it may not pass the inversion out correctly.
Sure.
Meaning, remember this issue? We had B, we had A, we had the capacitor. But when B does not equal to, or B equals 0, where this is off, and it doesn't pass,
It holds charge in there.
and it holds charge, so you don't know what state it is. Do we have that same issue here?
No, this is connected back to that B over there.
Yeah, because of the C inverted is already given its own logic, so we don't have that issue.
Yeah.
So that's like a problem he would ask. Yeah. All right. Since you're already here, can you do the complementary? Thanks. So does everybody understand what I mean? So because here we have that issue when B is not on, right? So your faucet is off. You don't know what the bucket holds because you don't know what it was in the previous state, right? So then we had to create a logic where it was something like this. We had B inverted to B tied to Y. So we could get that correct logic back out, right? But in this case, this already has a branch for C, not. So we don't have that issue, because then we don't have that issue of, okay, when B is off, where should it go? Because when C is off, B has somewhere to go. So we don't have that issue. All right, good job. Yeah, okay. Cool. Good job. All right, so I want 2 input XOR. Or let's do a 2 input OR. Let's do an OR. So it should be all right, Brave Souls. Any Brave Souls? This one's a little trickier because there's no obvious ands. So I will take Mirage. Oh yeah, you guys are both sitting in front of each other. That's funny. All right, cool. They're both Mirage. All right. I totally forgot. Yeah. So, what if it was a knot?
Is he not?
Yeah, if there was an A knot here, then you encountered the same problem as here, right? If you have A knot, then you don't know what's stuck. Okay, so it's a little flip. If you have A knot, right, controlling, and the gate is shut off, the faucet is shut off, you still don't know what's going on at this point. Does that make sense?
Yeah.
So we have to create some form of logic for A knot. So I could give you a hint.
Okay.
All right. So our hint could be, all right, so we know we have to do something here. Take this and let's switch colors. So let's say we know it has to do something with here, right? And we have to make some BS logic. Like this one has this BS logic of B naught, right? So we have to do the same thing here. So what we could do is A, and then we could do, yeah, and then you could create a pathway for A naught A, plus B naught. You could do that.
So we got 4 then?
You would have 4 if you want to. That's one way, because you already started off here.
Yeah.
Yeah. Yeah, so the logic you have here is A bar A, and this one's B bar B. So then, yeah, one of them has, or yeah, and then this one too. Yeah. Yeah, so that's the same. That works too. So there is another way, if you guys could find some Boolean logic, maybe if you're the circuit designer and you could call in another input, you would call in that other input and falsify it in here, like a C or something. But this would be workable fine. This is fine. Good job. All right. Let's work off of this one. All right, let me think what I could do to this. All right, so I want, all right, can I have a volunteer do an XOR? It's going to be Y equals AB plus AB, I believe. Yes. Can I have somebody come up to do an XOR? Anybody? I'm gonna pick on a girl because I have too many guys. You guys answer too many questions in my office hours. I feel bad I'm picking on you. Any volunteers, please? I don't like picking on people. Yeah, yay. Thank you. Saved us a lot of awkwardness. That's okay. Everybody's unsure the first time. So like I'm saying, you guys are first-time circuit designers, so I don't expect things to be the most efficient. So it's okay. You don't have to tie it all the way up. You could just put it right on top. Yeah, it's fine. All right, good job. So do we have that issue that we have here, where once you have your control is off, do you have an issue? Yeah, because, I mean, yes, and you're correct, because there is a B-bar path. All right, so pretty good. I want an XNOR gate now. All right, so the XNOR gate is really cool. Something about PTL that's really cool is, can I move over a little bit? So a really cool thing about this is why we kind of tie them over to the side a little bit. Can I borrow that? We tie them to the side a little bit so we could do this. And it's going to be, they're not going to be tied, my bad. And it's going to be A bar A. Just invert the input. Tie that down, tie this down. And then this is Y for XNOR. And this is XOR. So it's exact same design. Just make sure, so this area is exact same design. All I have to do is flip the inputs. And that's a really cool thing about PTL. All right, is duality. All right, so can I get another volunteer? Turn this into CMOS. Leanne. Oh yeah. Yeah, they're split. Oh, sorry. Yeah. There you go. Switched. All right, can you turn these into complementary? And what is the reason why we need complementary? Yes, but better in what sense? To make it have a good 1 and a good 0.
Oh, like a C.
Yeah, it's exactly like a CMOS. Complementary MOSFET logic, complementary PTL logic. All right. Yep. And then do the same for the top. Good job. That's fine. We all know what it is. Just put a little circle. Yeah. So one of HP's pet peeves is not having the circle on the PMOS, or not having transistors look like transistors. So it's really funny. Okay. Let me see, what else can we do? Other than that, there's not much I could say for PTL. So I know it was really confusing when he went over PTL for the first time, because now you have to introduce the drain as an input channel. And if you think of it, it's kind of like a bus. Like this line is that bus for that A. You could put other like transistor following down that line, and that would just be A busing through that line. All right. That's why I'm saying when you come up with logic like SRAM, DRAMs, it's starting to get a little flip-floppy. I think the basic one for, I forgot it was S or D, is you have like an input and then you have a cap here and a cap here. And it's, you could switch them on and off, and it's basically that Y is going to be stored in this cap or this cap, and it just goes back and forth based off the current and the status of the transistor. But PTL is very easy. All you have to remember is, okay, first thing is always look at the gate, all right? Always look at the controller. Just the controller when it opposes the opposite, meaning like B, if we have B going through here, when you have B bar, is it stuck at that imaginary capacitor? Remember that capacitors are parasitic capacitance of a transistor. It's not a real capacitor that we have there. It's similar to when you have the inverter and you have the cap coming off to the side, similar idea. All right? So will that be passed through? Or will B bar pass through? What will happen if you shut off the faucet? And in that case, you could imagine a capacitor at the line. It's like, okay, we don't know what's in that bucket. There's no pre-charger. We don't know what the previous state is, so we can't particularly say. But if you have something like here, and you have that path for B bar, and you're forcing that logic, you don't have that issue. All right? So of course, look at your gate, see, is there a opposite logic, like C bar? If there isn't, then you have to create that false logic, where you put B bar connected down to B, and let B bar control something. Yes?
Is it also possible to do on the left A and B, and then have A connected to B bar and have B connected to A bar?
Yeah. Wait, for this one or this one? This one.
For the XOR?
This one?
No, for the XOR.
For the XOR.
Yeah.
Yeah, and what do you want?
So if you have A and then the gate is B bar and B the gate is A bar, is that possible?
Yeah, just flip them around, that's fine.
Okay.
But also, if you do that, make sure your gates have something to control. In this case, if your gate is A or A bar, they're both controlled. Like A bar has a logic, and you won't get stuck with this issue right here. You get what I mean?
No.
So if you have A in your gates, right? You'll have A and A bar. You won't have that issue where when you have A bar, you don't know what's in that capacitor because A bar is given that logic anyways.
Okay.
Yeah. So when you do have that issue, put that false logic for that gate. All right. Just have A bar times A. That's fine. Just make sure it's an or, not an and. Don't put it right after each other. That's not how it works. All right. Another issue is complementary, of course, which is reversing for that good 1 and 0, and this complementary PTL, so it's C PTL. Then you need that C bar. So let's say you're in a test, we ask you to do PTL, which is really common. Then do the complementary one just to be safe. All right, do it as best as you can. Don't just half-ass it. This is your final. All right.
So do use CPTL when you're asking for PTL.
Yeah, because I mean it's your test. Do it as best as you can. All right. But most of the time, we're going to just give you PTL logic, like when we're giving you a problem. Yeah.
Would we have a question with 2 transistors in series for PTL?
Yes. 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 That is an issue. Like I said, it's a bus. So let's say you want another logic for A bar. Let's say you have something else with A bar. Let's say we'll have plus A bar C. Then you don't need to create or. Let's see. Yeah, so you have AB and AC or something crazy like that. Then you could create it across another line. And then of course you could have a break off of, let's say you start off here and you have like A bar, B or C, or A dot B, C and D, something like that. And you have, it could have A here, you could have B here, then you could go across and have C or D and reconnect them. All right, and that will give you that OR. And you could continue on, yes?
Well, how would you tie that back to A so you don't have that capacitor charging issue?
Then you create another line of just A bar. Or actually, the capacitor charging issue is because B doesn't have logic and B bar doesn't have logic, C bar doesn't have logic, and D bar doesn't have logic.
Yeah.
So then you're gonna have to have C bar, and you're gonna have to have D bar, and then you're gonna have B B bar. And you can fix that capacitor charging issue. And that all equals Y. Alright. So this is a case of how it's in series and it's in parallel after you already have one logic. So you can see already that some certain logic is smaller than CMOS logic. In the case of if you want XNOR versus XOR, all you have to do is flip your inputs. You don't actually have to create this. And then it's a matter of just rerouting lines. You would much rather reroute lines than call new transistors. Any other questions? We good on PTL? Please study memory logic. I beg of you, please. It's like always on that test. Everybody